So these questions are now linking nuclear physics to, or the decay, to what's actually going on inside the chemical equation. So the first question I got us to think about was the one about stability and that graph from last lesson. Okay, and what I'm looking for here is that we identify that initially we have 1 proton to 1 neutron, and then as atoms get bigger, it gets more like 1.3 is to 1. Now it's a very approximate way of writing it. I just wanted you to identify that the amount changes, it's not linear, but there is a relationship between the two. The second question, question 4, to define the term stability. Now, the stability depends on the context, but in a nuclear context, we're talking about the fact that the force that affects the neutrons, so the two forces which are the strong nuclear and the electromagnetic force. There are two other forces. One that seems to be playing a very, very strong influence on young Luke's socks.
Gravity.
Gravity is that one. So Luke, can you please fight gravity for 1 second for us, mate? The other one is the weak nuclear force. It's inside the atom, but it's beyond us right now. The last question, question 5, is to explain the conditions required to get certain types of decay. So we've got alpha decay and beta decay. So for alpha decay, you need a big atomic number. What's a big atomic number mean? You've got a big, heavy atom. So the atom is too large. The electromagnetic force pulls apart the atom. So electromagnetic force wins in alpha decay. In beta decay, we have too many neutrons. So to make itself stable, it will shed an electron and turn a neutron into a proton. That's the sort of decay we see in carbon-14. Clear? Let's look at question 6 where we've got a chance here, and then we'll give you an Ohm's law 1. So question 6. These are all examples of nuclear decay. So they're all examples of nuclear decay. The first one is what? What's the element on the left? 6A. It's carbon-14, which is used for? Carbon dating, radiocarbon dating. Waiting. It's very important that we conserve mass and charge. So the first thing I do is ask, is my mass the same? On the left and the right. What's my mass on the right? Left, sorry. Harper, what's my mass on the left?
6.
That's the element. What's my mass?
6.
That's the number, the atomic number. My mass is 14. What is my mass on the right?
14.
So I simply say, what do I need to add to 14 to make it equal 14? 0. Very good. Now, my charge. I'm just going to simplify this. Don't worry about the electrons at this point in time in each atom. I've got 6 protons here. I've got 7 protons here. What do I need to add to 7 to make it equal 6? Negative 1, or an electron. So I put negative 1 in. I know that that is an electron. So that is how I go about solving question 6A. Same thing for question 6B. What is my mass? Thank you, Julian. On the left. 235. What's my mass on the right? 231. What do I need to add there, Bevan? 4. Now I look at my charge. Brenda, what's my charge on the left? Charge on the right? What do I need to add? 2. What type of decay have we got?
Alpha.
Alpha. We write it as a helium particle.
That's what it is.
That's exactly right.
And alpha decays are always a helium particle.
Yep.
Yeah, because it's always 2 protons.
Yeah, we don't draw it as like the alpha sign. Okay. The only one you might see is gamma. Oh, I can't even draw gamma. And gamma decay is going to be expressed in question C. This is an example of gamma decay. This is what occurs inside of uranium-235. We fire a neutron. It becomes momentarily unstable. We ignore what happens afterwards. It becomes U236, and then it decays. 89, 36 krypton, 3 neutrons. What was left over?
144 mass and
So 144 mass, 56 protons, which makes that.
barium.
We sit down for an hour.
How is that gamma decay? Like,
Because it releases energy.
that's all it's saying.
Yep.
So,
Gamma decay is just energy.
so why in there's a question in this worksheet where it's
Oh,
beryllium to beryllium.
Yep.
Why is it releasing?
An electron. Is it?
It doesn't have charge. It's question 6.
Yeah, I'll come around and give you a hand in a sec. Just before we finish,
Is that an actual isotope or did you just make that up?
it could be an isotope. I haven't looked at the periodic table.
Yes, it's nice.
Yeah, but like, is it an actual
Yeah, that's the reaction. That's the reaction. Shh. All right. What should you do with a sick radio physicist or nuclear physicist?
Kill him. Leg.
If you can't, helium, try curium, and if that doesn't work, you might need to barium.